Hello everyone and welcome back. In this video we'll take a look at the CMSIS DSP library. Specifically, I'll walk through the installation process on how to get the library up and running in an STM32 project, and then I'll give a quick convolution demo using it. So, what is the CMSIS DSP library? Simply put, the library is a collection of the most commonly used mathematical operations for signal processing, and even some that aren't so common. Functions to implement matrix and complex number operations, FIR filters, Fourier transforms, PID control, and much more are all included within the library, all of which are optimized for ARM-based microcontrollers. So, in future videos when we look at implementing FIR filters or performing a Fourier transform, we can make use of the library, which will save us lots of time and guarantee that we are implementing the processes in the most efficient manner possible. To import the library into a Cube IDE project, we will need to download the necessary files. These can be found on the STM32G4 repository. If you're not acquainted with it already, each of the different STM32 chips has its own repo, complete with example projects, libraries, drivers, source code, and more. In our case, we are interested in the CMSIS DSP library, which can be accessed under Drivers, CMSIS DSP. Here, we can find all the files that may aid us in using the library. There's example projects, scripts, the library source code, and even a Python wrapper allowing rapid prototyping of algorithms within Python. For our purposes, we're interested in only two files: the ARM math header file, which can be found under include, and the precompiled library file containing the executable source code, which can be found under libgcc. These are the two files that we will import into the Cube IDE when we wish to use the library. To get started, I'll now download a copy of the STM32G4 repo. With the extraction complete, I will now grab the two folders containing our files of interest and place them within a new folder labeled DSP Drivers. This will be the folder I add to projects within the Cube IDE when I wish to make use of the library. With the necessary files prepared, I will now open the Cube IDE, create a new project, and, as always, initialize all peripherals within their default mode. Next, without changing any hardware, I'll transition to the C perspective. Within the C perspective, we need to perform a few tasks to get the library installed and recognized. First, I will copy and paste my DSP drivers folder into the project under Drivers CMSIS. Next, I will navigate to Project, Properties, C++ Build, Settings. Within this menu, we must perform 3 actions. 1. Add the include folder to the path. 2. Add the name of the library file to the library linker. And 3. Provide the path to the library to the linker. First, under MCU GCC compiler include paths, I will add the path to the include folder. Second, under MCU GCC linker libraries, I will provide the name of the library that we are using. In this case, it is ARM Cortex M4LF Math. Lastly, I will now add the path to the library. With those 3 steps completed, I will apply the changes and close out of the Project Properties window. Finally, the last step is to add the .h file. At the top, under User Code Includes, I will include the ARM math header file. Now, as an example, I will walk through the implementation of convolution, which, thanks to the library, is a relatively simple affair. Before we begin, let's first look at the documentation available on the CMSIS DSP website. Convolution can be found under Reference Filtering Functions Convolution. As can be seen, this site is quite thorough, and the math equations are provided, and so is an explanation on how to call this function. For this example, I'm going to perform convolution on 32-bit floating point numbers, which require 5 input arguments: the pointers and lengths of the 2 input sequences, and a pointer to the output sequence. Starting from the top of the main.c file within the Cube IDE, under the user code private variable section, I will define the 2 input vectors a and b and the output vector c. For simplicity, I will set a and b as a ramp from 1 to 5. Next, within the user code 2 section, I will place the convolution function and enter the required arguments. Now, I'll build the project and switch to the debug perspective. Lastly, under live expressions, I will add the output array C and run debug. We can now observe that the variable C has been populated with the results from convolving the A and B input vectors. And that's it. Thanks everyone for watching, and stay tuned for the next video where we will take a look at implementing FIR filters. Thank you.